This is Turrimetta Headland in New South Wales in 2015, a towering heap of faulted, fractured Newport Formation sandstones and shales, capped at its highest point with a tiny remnant of Hawkesbury Sandstone, all of which rests upon the purplish Bald Hill Claystone unit that you can see at low tide. In 2021, Turrimetta Headland's cliffs were videoed from a drone, part of a record of the coastline from North Narrabeen to Barrenjoey. This publicly available footage is a baseline against which future geomorphic events, rockfalls in particular, can be identified and measured. However, there's an earlier video that was shot in July 2012 of a Pittwater Natural Heritage Association walk and talk at Turrimetta with geologist Dr. Peter Mitchell.
These are all ironstone, that's shale, and that is coal. The coal came in as logs around, loaded with 1.5 kilometres of sediment, round logs become flat slab.
Mitchell paints geomorphic pictures on a broad Australian canvas, referencing Indigenous prehistory, geology and paleontology among other disciplines. His tools are scientific rather than sable-haired, his reasoning compelling. In this 2021 screen capture, near where Mitchell showed us the piece of coal, we can see 2 joint blocks missing, plucked from the basement rock by wave action. But by 2025, 5 blocks are missing, so 3 more were removed in just 3 years, a rate of around 1 block per year, and a steady undercutting of the cliff above. Further, just to the right, the same 2025 screen capture shows large boulders on the platform that were not there in 2021. They have fallen pretty well on top of the labyrinthodont footprints that the Pinhar Group and Mitchell were looking at in 2012. They would have suffered a direct hit by a couple of boulders weighing around 10 tonnes. It's also worth noting that the footprints, clearly visible in 2012, are now covered with boulders that are frequently moved around the platform by large seas and even, on occasion, swept away entirely. If we freeze Mitchell as he walks by this boulder, we can see in the middle distance a pile of rocks, an earlier rockfall, indicated by the arrow. Remember, this is 2012. But in this 2025 picture, we see that same fall pretty well unchanged. We can clearly see that the edges of the boulders are all sharp, unworn by time. We can't be specific other than to say that this fall is also quite recent, though before our record. But when the camera pans left, it shows something that wasn't there in 2012, a very large rotational rockfall of perhaps 200 cubic metres. Now this fall is also visible in the 2015 drone footage here. So this rockfall dates between August 2012 and December 2015. Mitchell and his students were lucky. But how lucky? They probably spent around 10 minutes in the danger zone. The ratio of 10 minutes in 3 years is about 1 in 150,000. But in that 3 years, hundreds of people probably made trips along the rock platform, likely increasing the probability of being exposed to a fall to perhaps 1 in 100. Though that figure does not take into account that people don't walk the platform at night. On the other hand, rockfalls are most likely to occur during inclement weather, when rainfall is heavy and seas high. Good times to stay away. Furthermore, where the fishermen were walking in 2021, there is another small collapse of perhaps 6 to 8 tonnes, and yet another a bit further on. All these falls can be recognised by the freshly exposed rock face and confirmed by comparison with the 2021 baseline drone footage. Which brings us to the sewer outfall where fishermen and women congregate. Construction of the outfall was completed by about 1973, so the rocks you can see here in 2021 must have fallen later than 1973 because they rest on the concrete covering the sewer. It's also pretty clear that all these rocks and boulders comprise a multi-fall event which is, perhaps, ongoing. The May 2021 reference flight shows the precarious position adopted by fishermen. Since this footage was taken, 2 fishermen have drowned here, swept from the platform by waves in January and again in December of 2022. Indeed, this footage may show those people, but we don't know. This is the earlier 2015 flight of the 19th of December. As the drone rises to return home, just as it sets out, if we freeze the frame, we can get a good look at the point and the rock platform. Note there are 4 boulders on the platform that have obviously fallen from the point. But the reference flight of the 22nd of May 2021 shows an additional fall. There are now many boulders. And just 3 weeks later, by the 13th of June 2021, we've had a huge fall on top of the previous 2. This fall has completely removed Turrimetta's nose. The inherent instability of Turimetta Headland is exacerbated by the rapid retreat of its Bald Hill Claystone foundation. We can get a good idea of this where more than half a metre has eroded from under the edge of the concrete that was poured on top of it in about 1973, which gives us a rate of retreat of about a metre a century, or 1 centimetre per year. The view from this angle shows just how unstable Turrimetta is. Not surprising, seeing that it aligns with, and is almost certainly part of, the Lunar Park fault zone. As the camera goes around the point, the rock platform comes into wider view. If we freeze the frame here, that crack you can see running across the rock platform towards the cliff is a slickened sided fault where rock has moved against rock, polishing the faces and leaving lines that indicate the direction of movement. The dip of this fault is about 75 degrees north. Some of the fault plane is curved and there is a wide crush zone at the base. And if we reverse the camera, we can see how the cliff is intersected by the fault and how the southern face has already partially collapsed. But in reality, fault planes are often curved surfaces, so multiple faults in sedimentary rocks intersect and can pass into bedding planes, making the three-dimensional patterns of failure very complex. These intersecting fault planes create more intense rock fracturing, which is concentrated in areas referred to as crush zones. Crush zones become significant weak points when exposed on a cliff face. So on Turimetta's south face, we have serious undercutting along the inclined fault line, and on its eastern nose, massive random fracturing that is opening up, simultaneous with extreme undercutting of the north face. These opposing undercutting processes must eventually intersect. Shot through with cracks, faults and fractures, and undercut on this north face in particular, Turimetta appears to be teetering on the verge of a major collapse. Will it all come down in one event, or just continue as it does now with frequent little falls and the occasional big one? Don't stand around too long, or you may witness something you'd rather not see.